Pleasure of introducing who I'm sure you all know, Katie. She's a lover of sea pigs because they look like vacuum cleaners on legs, and basalt because it makes up the majority of the ocean crust. She received her Bachelor of Science in Geology from the University of Miami. Then her Master's in Marine Science from UC Santa Barbara. Then went back to Miami to receive her PhD in Marine Geology and Geological Physics before doing her postdoc at the Monterey Bay Aquarium Research Institute. She enjoys anything that has to do with water or the ocean, and though she's not scuba certified, she does enjoy snorkeling. Her favorite game to play is called Killer Bunnies and the Search for the Magic Carrot, a game of which once went on for over a week. She believes that pineapples do belong on pizza, especially with Canadian bacon or ham. And her favorite pachyderm is the elephant, which is the correct answer. If she were dropped in the middle of the woods with no tools but a compass, she would head east first. She prefers haikus over tankas and 3 dimensions over 2 dimensions. She also wants to make explicitly clear that hot dogs are not sandwiches. She currently lives in Monterey, where she is an independent postdoctoral researcher, except in the summer when she tries to convince a bunch of science kids to become geologists. Everyone please welcome NYSC's own Dr. Katherine Inderbitzen.
Thanks. Thank you, Addison, for that fabulous intro. Let me see if I can get this fixed on here. Maybe we'll see how loud I get. Everybody hear me okay? Yeah. All right, I'm pretty loud anyways. So, all right. So we're going to talk today about the deep sea, the seafloor, what's underneath the seafloor, which you've probably never even thought about before. So if I were to say the deep ocean, how many of you would be completely terrified? I'm just really curious. Okay, a good number of you. Okay, hopefully I can cure you of that today. Well, we'll see, because the deep sea is probably one of the most amazing places that we have not explored left on the planet. So, who am I? Not Jean Valjean, I did not steal bread, but I am a scientist and I am an artist. I've spent basically the better part of the last decade and a half working at sea, under the sea, in a variety of different kinds of vehicles, which I'm going to elaborate on today, and also making really awesome costumes. So, oh yeah, and so if you heard me talk about the embarrassing photo of me at 14, that's me. At 14 in Hawaii. With the Jason Project, I was involved in the Telepresence Project. We basically broadcasted live research to museums across the country. This was in the 1990s, so that was a big deal. The internet was not very fast at that point in time. You still had to do that awful dial-up noise, that yeah. So that was a big deal. But anyway, that's me in a nutshell, not really. So mostly when we think about the ocean, you guys probably think about images like this, right? Coral reefs, snorkeling, beautiful clear waters. Well, most of the ocean does not look like that. Most of the ocean is dark, okay, and you can't see anything. This is just restricted to the upper couple hundred meters of the water column, okay? And it's amazing when you're falling through the water column just how quickly the light goes away. It's very, very fast. Okay, so you've probably seen some headlines that look like this, you know. We know more about the backside of the moon than we do about the floor of the ocean. You know, these are things that are pretty prevalent now, and they'll pop up every so often. So there's a lot of truth to this. And really the reason is because the ocean floor is huge. And to map it at a usable resolution is very, very, very difficult. But you might say, but Katie, this map exists. This has all of the mid-ocean ridges. This has all of the trenches. This has all of the seamats. So yeah, we mapped the ocean floor. Yeah, cool. Yeah, we're done. Yeah, we can go do something else. The issue with this is resolution. Okay, so how we made this map is using a satellite. Okay, and the interesting thing about satellites and mapping the ocean floor is that satellites cannot penetrate water. Okay, to do mapping. So how these were made is actually little mounds of water mound up over high points. There's little dips at low points, and so there's an algorithm to correct for that, and we can get a decent map of what the actual seafloor looks like. But our resolution is 5 kilometers, okay? 5 kilometers, think of a pixel that's 5 kilometers wide by 5 kilometers high. So anything smaller than that is not going to be visible. And here's a good example of this. So here's the base map of an outcrop that we surveyed in 2013 and 2014. It's off the coast of Costa Rica. It's called Dorado. So this was the existing map when we went out there, and we went out with a vehicle and were able to go from 5 kilometers resolution to less than 1 meter resolution, okay? And the issue with this becomes is that to do this kind of a map, and this is a pretty small area, to do this took a couple of weeks. Okay, so you can imagine that mapping just this tiny corner of the seafloor was extremely difficult. Okay, so if we wanted to do that for the whole ocean, okay, let's say we wanted to image and map the entire ocean, we would basically, if we were doing it with a ship, we'd have to go mow the lawn, just like you mow the grass, go back and forth and back and forth and back and forth over an area, and that's going to take a really, really long time. Even if we're just doing it with sonar, it takes a long time. If we're doing it with a video camera, it takes even longer because you can't go very fast or else you don't see anything. And then what's the point? So how do we actually start to look at the seafloor in a more usable way? Okay, so we're going to go from less human intervention to more human intervention with vehicles. So we're going to start off with AUVs. These are autonomous underwater vehicles. So these are your robots, okay? These are things you can program, you can tell them what you want them to do, and then you can put them in the water and they will swim away and do their job. So there's minimal human intervention really needed, except up front and to put it over the side and then to pick it up later. And so this is probably the most well-known vehicle right now in autonomous work. It's called Sentry. It's owned by Woods Hole Oceanographic Institution. I've got a picture in a minute that you'll see more of. It's pretty cool. There's also wave gliders, which is the one on the upper right. That's a Mambari wave glider. Basically, it sits at the surface and it glides along. It can collect atmospheric and water data at the same time, which is really cool. And then there's other things like the one that looks like a missile down at the bottom, which they can do sometimes fluid sampling. You can program it to take a sample every so often at different depths, things like that. The neat thing about Sentry is that we can actually put things on it that will sniff out chemicals. So we can put on a mass spectrometer and we can say, we want you to look for this one thing, and it will go out and it will sniff for it. And I'll show you in a minute how probably the best case that we've done that in. So the other fun thing about Sentry is there is a guy who just puts a face on it every cruise, depending on what the cruise is about. So the one on the left, Sentry had a stick poking out of it. It was a new instrument that they were testing, and so it looked like he was jousting, so they made him look like a knight. And then the one on the right is from one of my cruises. It was at Christmas time, so instead of Sentry, we had Sentry Claus. So yeah, there's a guy who part of his job, he does the programming, but then he also makes cool faces on the vehicle, which is really fun. So probably the most famous thing that Sentry is well known for is work on the post-Deepwater Horizon response at the end of 2010. So basically there had been all of this work on the surface oil slick that was happening, but the real question from the scientific community was, is there a mid-water plume? Where is it? Where is it going? Things like that. And so they were able to send Sentry out with a mass spectrometer aboard and basically create this 3D map of the plume so they knew exactly where in the water column it was and how far away. And this was really at that point when they entered it into the facility, because it had been kind of on the fence for a while, which was pretty cool. Okay, so now we've got our autonomous vehicles, cool. What if we want a little more human involvement? Then we can move to an ROV, or a remotely operated vehicle, okay? And this system usually is a two-body system, because if you think about it, the ship's going up and down, it's really bumpy. That's going to make your vehicle go all over the place, right, if you just have it connected to the ship. So if you have basically what we call a clump weight or a drop weight vehicle in between, that vehicle will go up and down, but when you connect your ROV to that, it'll be mostly free floating and unaffected by surface waves. So that's why most systems like here, this is the Kaiko from Jamstech, which I've used, and the one on the upper right is Hercules, which if you've ever watched Nautilus Live on nautiluslive.org, they do live exploration footage. That's the vehicle that they use, and I've gotten to use that one as well. So basically, the great thing about ROVs is that they can dive for a really, really, really long time because they're attached to the ship. They have a permanent power source. So Jason, for example, which is Woods Hole's ROV, has had, I think their record is 96 hours for a dive length. And so you're working around the clock, which is pretty cool. You work 4 hours on, then you get 8 hours off, and then you work 4 hours on again. Let me show you how these get launched. So this is an example of the Hercules being launched, and it's time-lapse, so it's pretty fast. So they always launch the vehicle first, and then the clump weight goes second. It's just easier to do it this way with how the system is set up. But so see, they're putting it over the side, and then it'll drive around to the stern of the ship, and then they'll lift in the other vehicle, which they call Argus. And Argus for them actually has a dual duty. It also has extra lights on it and stuff, so they can really light the area that they're exploring, which is super cool. Okay. Click. Okay. So the other great thing about ROVs is that lots of people can be involved at once. You're not restricted to like 2 or 3 people. So the control van for one of these things basically is just a wall of monitors. So the pilots basically have to create a 3D perception in their head of where they are on the seafloor using all of the different camera angles that we get on the monitors. But we can have, 10 scientists in the back, working on collecting data or collecting a sample. The other great thing is with the advent of better internet and better satellites, we can actually live broadcast ROV dives direct to you. So I mentioned Nautilus Live already. That's nautiluslive.org. I am plugging them so hard right now. Also, the NOAA. NOAA has another program. It's on the Okeanos Explorer. Both of them have Twitter accounts, and they always tweet when they're going to have a dive. So like you can just be like, oh, I don't have anything going on today. I can put this on, on my other monitor and just kind of look over occasionally and see what's going on the seafloor. It's very, very cool, and it makes science really accessible to the public. And it's really interactive. You can ask questions of the people who are on the ship, things like that. Okay, and we call that telepresence. Okay, so now we've gotten to the uber human intervention vehicle. So we're dealing with HOVs, human-occupied vehicles, submersibles. Okay, so these are the really cool things. You get to go in and go down. That's the best part, wink wonk. So this is a classic image, right? So William Beebe, back in the day, decided that, yes, a sphere will distribute the pressure the best. So we're going to build a sphere, and we're going to get in it and get lowered down on a cable. That is basically, minus the cable, what we still do today, okay? Just new technology, but the same concept. So the one that I have the most familiarity with, there are a lot of research submersibles in the world. Well, not that many, but there are a few. Is Woods Hole Oceanographics Alvin submersible. Okay, this is the submersible that explored the Titanic in 1986, yes, okay. So Alvin's been in operation since the 60s. It's had a lot of upgrades since then. We just went through a $25 million upgrade about 5 or 6 years ago, which is great. It's given it much more depth capacity. So it used to be that we could only go down to 4,500 meters. When we finish the upgrade, we will be able to go down to 6,500 meters, which means we will be able to access 90% of the ocean floor, which is really significant because when you can't get to places, it's really hard to explore them. So some stats about Alvin: it's really heavy. The sphere is made out of titanium. The new sphere is about 6.5 feet in diameter. So if you want a good example of what it's like to be on a dive, that's a picture of me on my first dive with my colleague Bob Meldrum, and then on the right is actually my boyfriend now. We weren't together then, but this is how we met. the best analogy I can come up with for diving in Alvin is being in a broom closet with two people you do not know for 9 hours. And one of two things is going to happen. You are either going to, at the end of those 9 hours, hate them or be best friends. And that is exactly how dives work. And you really have to work together. There's 2 scientists, 1 pilot. It's a 9-hour dive. The Navy owns the sub, so we're only allowed to dive during the day. We go in the water at 8 a.m. We have to be back on deck by 5 p.m. So that's one of the things that constrains working with submersibles is you have only 9 hours, and that includes your transit time. So we use the power of gravity, gravity, to fall through the water column, get to the bottom, go around, do our work, and then we have to release our weights and use our neutral buoyancy to rise back up to the surface. And so you really got to make sure you can get all your stuff done. So you got to have a really good dive plan, you got to have efficient people in the sphere, you got to be ready to work. Okay, so, oh, these came out okay. Yeah, they look good. So Alvin is, as I said, really, really big. So getting it off the deck and into the water is a really complex process. So if you look at the width of the rope that goes around the lifting tee, you can get an idea of just how hard it is to lift this vehicle. When they actually took it off the ship and put it on shore, they had to get like a special crane from somewhere because nothing else could lift it because it's 35,000 pounds. And they didn't have anything in Woods Hole that could deal with it. So I think I should have a video. Yeah, so I've got a time lapse. Basically what happens, the sub sits in a hangar for most of the time, and then when we're getting ready to dive, it gets rolled out on these tracks. They strap the weights on. The scientists climb up the stairs, get inside the sphere, everything gets closed up, and then they get lifted off and into the water. Okay, and it's really cool. Like, I'm not gonna lie, like, this is the coolest stuff I've ever done. Okay. Okay, where are you going? Go. There we go. Okay, so why would you choose an ROV versus a submersible? Okay, so this is one of those times. So this is the ROV Jason footage. They basically went out to an area. They were going to be doing pick up some lava, do all kinds of exploration stuff. And they got there, and the volcano was erupting. Okay, this is a situation you do not want to have people in. Okay, so these are the situations when you really want to have a remotely operated vehicle because there is no danger. At one point, the bottom of the vehicle got covered with elemental sulfur because they accidentally sat down in a pool of sulfur. And so they brought it back up and it was fine, but if that had been a submersible with people in it, that could have been really, really, really bad. So in this case, especially where we have explosive undersea eruptions, which are not necessarily terribly common, we believe now that they're more common than they used to be. Well, we believe that they're more common. We didn't think they used to be. Let me rephrase that. So that would be when you would want to use an ROV. The only thing is, well, another thing that's really important is these things are expensive. Okay, so the day rate for Alvin is something like $35,000 a day, plus the ship, which is I think another $15,000. Jason is also pretty expensive, but that gets built into your NSF budget. And also, what's also really important is that there is no replacement for having human eyes in the field. Okay, so yeah, you could be using a robot and looking at tons of screens, but it's still different. And now that I've done both things, it's a completely different experience to actually look out the window and have the 3D all around you. Whereas, if I'm sitting in the control van, it could be halfway across the world and I wouldn't even know. So for me, having that 3D context means a lot if I'm doing field geology, if I'm trying to understand an outcrop that no one has looked at before. So how do we access then? How do we access the subsurface? Okay, we've already seen that accessing the deep sea is hard. Okay, so how do we get into the subsea floor? Okay, that's like a whole nother level of hardness, right? So then we need to use scientific ocean drilling. Okay, and this is not oil drilling. We're not allowed to go where there's oil. Like, that's not a thing. So IODP, which, how many people read about the deep sea drilling program in science class at some point? Deep sea drilling program, Glomar Challenger, something like that. Yeah, maybe, okay. The same program still exists today with a different ship and a different name, but it still exists and they are still trying to figure stuff out. So we have 2 ships in IODP now. We have the JR, the JOIDES Resolution on the left, and the Chikyu, which is owned by Japan, on the right. And these ships are how we access everything inside the ocean crust. Because what we can do is we can drill down through the sediment and get into the rock and really find out what's going on. Okay, so I'm going to move into kind of a little case study of something where we've used both vehicles to get to the seafloor and subsea floor ocean drilling in order to really look at a large-scale question. And the case in this, and the question here was, where is the heat? So it turns out that when the mid-ocean ridge forms new crust, remember it spreads apart, conductively, that heat that's removed as it cools, turns out when we measure it with a heat flow probe, we don't measure everything that should be there. Okay, and this was a big quandary for scientists for a really long time, because there was a model that said that this should be how much heat is there, and we were only measuring this much. And it turned out that the thing that it was missing was advective heat flow, okay, which basically amounts to fluid circulation, okay, hydrothermal circulation. And so at the ridge crest, where there's no sediment, it's really hard to measure these things because there's no sediment to stick your heat flow probe into. You can't stick a heat flow probe into rock. So we do have a little bit of a sampling bias, but we were able to figure out that the fluid flow is happening and that it's probably what's accounting for that missing heat. It's not really missing, it's just we can't observe it directly. So fluid flow within the porous volcanic layer of oceanic crust may be one of the most influential yet poorly understood processes on Earth. We do not know how long it happens, how big the circulation cells are, what the general chemistry is. We really know nothing, okay? And I want to pass around, where did it go? Where is my basalt? Did I put it over here, or is it over here? Oh, thank you. Thank you. Okay. So, first off, I'm going to pass around a rock, all right? This is basalt. I did not collect this. I do not know where it is from. I'm sorry. So this is basalt. This is what most of the ocean crust is made out of, okay? And I want you to, when you get it, take a look at it. Look at the holes, okay? Just pass that around, okay? So, turns out that when the ocean crust is formed, there's a lot of holes in it. There's a lot of space, okay? And can anyone tell me the difference between porosity and permeability? Those are 2 different things. Yes?
Porosity about how turbulence the
Yeah, so exactly. So the difference is porosity is just how much hole space there is in something versus permeability, which tells you how connected those pore spaces are. Okay, so you might have something that's really, really porous, but not very permeable if it doesn't have any connectivity. Okay, so take a look at that when the basalt comes by. So we really, at this point in time, have very little understanding about how fluids flow around in the porous part of the crust. Okay. All right. Now, here's my clicker. There it is. Okay. But it turns out that the great thing about the seafloor is as the seafloor ages, sediment gets deposited, right? And it turns out that a big, thick blanket of cold, wet sediment sitting on top of a porous crust means that no water is getting out of that crust because sediment is very, very impermeable, okay? So you're not going to get any vertical flow through that sediment. So what ends up happening is the water needs somewhere to go and it needs somewhere to come from because it's removing heat from the crust. So what happens is these little rock nubs that stick up above the sediment end up acting as conduits. Okay, so some of them will suck in water, some of them will vent water, and this is not terribly hot water. It's, maybe 40 to 60 degrees C. Okay, it's warm, but it's not boiling. It's not hydrothermal vent level of like 400 degrees C. And this is important because it's controlled by the shape of the basement, or what we call the crust, underneath the sediment. And then the circulation cells, it turns out, are parallel to the ridge axis. Okay, so the ridge is going like this. The circulation appears to go along the ridge, not across it, which was the initial thing that they thought was happening. They said, oh, well, it's going to be, convection cells, kind of like you see in the earth science textbook in the mantle. It just looks like a convection cell. They thought it would be the same thing. Turns out that's not actually the case. And the great thing about that sediment blanket is it allows this circulation to potentially continue for millions of years. So we've found, 20-million-year-old crust that still has evidence of fluid circulation occurring. So this is something that can happen for a really, really long time. And that has consequences for the chemistry, for the microbiology, for the geology of the subsurface. Okay. And this is just another kind of better image. So some of the outcrops will suck in water. Some of them will vent water. But the question becomes then, how do we observe this? Okay, if we were to drill down, let's say, through the sediment layer, we would basically be short-circuiting the system. Because how we drill is we use bottom water as our lubricant. Okay, so that's 2 degrees C seawater. Okay, and if this reservoir is 40 to 60 degrees C, then you're going to completely mess up everything thermally, chemically. So the question in the scientific community in the early 90s was, how can we observe this kind of thing without disturbing it? Okay, and that's a lot of the time what you find in science is, how can we observe without disturbing? So what ended up happening is, conveniently, there was a workshop, and several of the scientists were at the bar after the workshop, and somebody drew a diagram on a napkin. I'm not even making this up. They drew it on a napkin, and it eventually became a cork. Okay, and so they came up with the acronym first, so they had to figure out how to make it fit afterwards. So it ended up being called a circulation obviation retrofit kit. And that's a lot. That's a lot of verbiage, right? So what that breaks down to is circulation obviation, stopping circulation, okay? And then a retrofit kit, meaning we could do it after we drill. Okay, we could go back and technically refit any hole that we've drilled into the ocean crust with one of these, so long as it's got a re-entry cone. And what it amounts to is what it sounds like. It's a cork. We literally put a big cylindrical unit down into the hole. We instrument it with chemistry sensors, pressure sensors, and plug it up so that we've basically re-isolated that reservoir that's inside the crust. And so now we can let it come back to normal because we've probably perturbed it with our 2 degrees C seawater. And then once it's gone back to normal, then we can see what the natural system is doing, okay? And so this was something that they worked on for a really, really long time before we actually figured out that it worked. Okay, so the project that I was involved with is actually, the first corks for that system went in 2005, the year before I actually started working for my PhD advisor. And we didn't really finish the project until 2014. Okay, so these are long-term things. These are, we're really looking at long-term background information here. And so what you're seeing on here, this is the business end, okay? This is the part that we work with at the seafloor. Most of it is underneath us, hanging in the borehole. But this is the stuff that we interact with. And so we have a variety of data that we can collect. Oh, this is the assembly. So fun fact, I am actually 8 years old. And yes, I wrote that on the cork. It says stuck in the A-hole because this was 1362A. So of course I had to make a terrible joke because I am actually 12. And we paint the corks so that we can tell them apart when you're on the seafloor because they start rusting pretty fast. And we want to be able to know which one we're at because they start looking real similar after a while. So we painted them, we assembled them below the rig floor on the drill ship. They get lowered down, they get put in the borehole. Then what happens after that? What are we collecting? Oh, wait, here we go. Sorry, there's a map. So these are the ones that we've put in for this particular project. So here's, if we were to take the sediment away at the bottom, this is the ridge that we think, or that we thought was controlling flow. We thought it was going from south to north. So we had a whole bunch of corks in a line because we wanted to see if we could actually track fluid moving to the north. And then we also had one out over here to see if there was any flow that went perpendicular to the ridge. So that was like our control, basically. And so, yeah, so some of these went in 2005. The ones that are marked SR2, those are the ones we put in 2010. Okay, so there's a total of, let's see, 1301A, 1301B, 1362A, 1362B, 1026. Yeah, there's a total of 6 corks out there. Okay, and these again are not cheap. Each cork costs about $1 million to put in. So these are expensive engineering marvels. Okay, the act of getting one of these in and getting it to work is phenomenal. 2 of them that we put in 2005 leaked for like 3 years because they didn't cement them correctly. So a couple of the first cruises I was on was like retrograde cementing, where we literally had a contraption that was a 50-gallon drum of cement that we took down with the submersible, and we tried to, it didn't work. We tried. A valiant effort was made. So this is where the corks are, and what kind of data can we collect? Probably the most important piece of data that we collect is pressure, okay? And we collect pressure at the seafloor and within the borehole, okay? And you might be thinking like, well, why would you collect pressure in the borehole? Like, wouldn't it just be the same? Well, it turns out it's not, because the crust, even though it is a rock, is compressible, okay? And so I like to use the analogy of the sponge, the dry sponge. So it's porous, it's got space, you don't think it's gonna squeeze, but if you really mash it good, you can get it to squish, okay? And in the case of this area, we have 2 kilometers of seawater sitting on top of our crust, okay? So the loading or the pressure that we're applying to that crust, what kind of changes in pressure do you guys think we would have out at sea over like a day scale? Maybe the tides? The tides? So like high tide, your water column is going to be a lot taller than your low tide, right? And it turns out in this area, we have a 2-meter tide, okay? So that's a huge tide. That's 6 feet. That's like a gavin, okay? Well, it's a little less than a gavin. But so if we are changing the amount of water that we're putting on top of the crust every day, that's going to be pushing down and lightening up on your crust. And so that also helps fluid flow around. I'm going to pass the sponge around so you guys can try to mash it and get the idea of how that we can actually compress the crust. Okay. So we've collected, so we can get our seafloor pressure, our borehole pressure. So it turns out that when we get a borehole pressure reading, we actually see the tide, okay? And it's just the amplitude of that tide is decreased as a function of the compressibility of the crust, okay? And I'm not going to go into that a whole lot, but it's kind of a neat thing. You wouldn't expect to see the tide inside the crust, but you do. And that was very surprising to them when they first started collecting pressure data. And so this is one of the units. This is like a backup unit that we installed on a broken cork. This one is one of the ones that ends up on the wellhead, and that's what it looks like when it's on the bottom. And we do have to physically plug into these things to download the data. And so that's where using submersibles and ROVs comes in, because we literally have to go down there, take a cable, plug it in. Which this should, yeah, here we go. So this is a different cork. This is actually a cork that I did my PhD at, or my PhD work on, but you'll get the same, you'll get the idea. We basically have to drive up to the cork. We clean off with a toilet brush, yes, yes. This is the most important thing we bring on cruises, is the toilet brush. I'm not even making that up. Because this is how we clean off our our data connector so that we make sure we're not pushing any kind of sediment or bacteria into the connection and potentially shorting things out. So we clean that off real good, and then we take our other side of the connector and we plug it in. And then through the hull, I'm basically able to talk to the data logger, with a computer, just with, Python, and say, hey, wake up, give me all your data. And then it downloads, and it takes a really long time because there's a lot of data. But the really neat thing actually is that for our pressure loggers, most of the pressure case is battery. Okay, so some of these have been out there for years and years and years. Okay, and they only wake up, once every whatever to take a data measurement. So 90% of the pressure case is battery, and then the actual logger part is 3 little cards that are this size. Okay, super tiny, and you're never going to guess what we store the data on. Compact flash cards. Okay, so not even an SD card, because it wouldn't handle it. It turns out it wouldn't handle it, so we had to go to compact flash. So the PI for the project actually went on eBay and bought up somebody's lot of 100 compact flash cards back in the day. It was pretty funny. So yeah, and then we sit there, we download the data. I can reset the memory, make sure it's clear, make sure the clock is correct. The clock is also really important because if we're having a lot of clock drift, that's going to change what our data look like. Okay, so we need to know all the time what our clock looks like. And this is also important in satellite work, but especially important in the deep sea. Okay, come on. There we go. Okay, so what other data can we collect with CORPS? We can collect continuous chemistry, fluid chemistry data, okay? And this is really, really cool. This is what the guy I worked on my postdoc with, this is what he developed. They're called Osmo samplers. They run using no batteries. They use osmotic pressure across a membrane, and that is it. They will run for over 5 years if you put enough salt in the reservoir, okay? So basically how it works is we create a salty brine on one side of a membrane, and then we fill our coil with fresh water. So basically the fresh water wants to go to the salt water, right? And so what that does is it sucks fluid into our coil, and we know the diameter of our tubing, and we know the rate that our pump pumps. So when we pull our coil back up on deck, we could say, okay, we know that 1 meter of this tubing is equal to 1 day of sample. So we can get 1 day resolution on chemistry sampling. So if we're looking at something changing over a long period of time, we can see oh, Monday it was like this, but by Wednesday it was completely different. That kind of thing, which is really important, and it was completely unheard of until Jeff really developed these in the 90s. And they're really great, and so we can put them outside the wellhead and just hook them up, or we can put them down inside the wellhead. These were some of the ones we recovered. They had been in there for like 6 years, and we have 2 kinds of tubing. Just the regular Teflon tubing is for just fluid chemistry, but if we want to do gas work, we use copper coils because it at least keeps the gases in solution and from exsolving. And the other great thing about Osmo samplers is you can also modify them to work for microbiology. So we have a lot of people, and this is a big developing field, so if any of you are interested in microbiology, deep sea subsurface microbiology is super hot right now, okay? Tons and tons of great, I'm not even making this up. The people who funded my postdoc are microbiologists. So what we can do is we can basically use one of these pump systems and use it to wash borehole fluid over cartridges of different minerals, of all kinds of things, and we can see where are the microbes, what do they like to eat, what do they like to grow on, do they form biofilms, and all of this kind of stuff. So they call them FLOCs, F-L-O-C-S, and I don't remember, I think it's like flow through Osmo sampler chamber system, I think. So they use one of these pumps and just basically bathe their samples in borehole fluid for 5 years, and when they get them back, they're completely altered because the microbes have come in and they've eaten what they want to eat and they've undergone their metabolism and all of that. And it's really, really, really cool. So that's something else we can do. Okay. Okay, so This is just like a little fly around I put in here so you guys can get an idea of like where things are on the wellhead. You can see we painted it. This one's, yep, that's my name. My name's on there. I did not not want to have my name at the bottom of the ocean. I thought that was a once in a lifetime chance, so why not? Let's go for it. So this side, actually on this one, if you saw the shimmering water, on some of these we actually built a ball valve into the side so we could actually vent the fluid coming out of the formation and look at how the pressure drawdown in the other corks around the area could tell us about, you know, what's the porosity, what's the permeability of the crust in this area, because it's very, very difficult to measure that in situ. Okay, we've tried doing it with a drill ship. It's not really great because you really only get a local reading, so we were trying to get a regional reading here. Okay. Okay, so what did we decide to do, you know, after we kind of had all of our corks in? What are we going to do next? How are we going to figure out what these flow patterns are? Is our assumption correct that we're getting general flow from south to north? Basically, we did a giant groundwater test. Okay, so who's familiar with like groundwater well tests at all? Or if you've heard about them, seen them. So usually you inject something into one well and then you have recording at other wells to see where things happen. So yeah, that's pretty easy to do terrestrially, right? Imagine doing it at the bottom of the ocean. Okay, so this was the first time this has ever been done in 2010. And we didn't really get any press about it because it was right during when they were trying to fix the Deepwater Horizon. And so the word drilling was a big old no-no, so we had no press for the entirety of our drilling expedition, which is really too bad because we did some amazing engineering. So basically what the plan was to inject a number of different tracers into one hole and then see where they ended up over time. Okay, and we can do that with these long-term chemistry samplers, etc. Now, so what did we inject? That's pretty important. Okay, so this didn't come out very well, so it was very dark, sorry. That was to show the flowing. So what did we inject? We injected sulfur hexafluoride, okay, which is a non-reactive gas that's often used in hydrogeology. This was the first time it's been used in the seafloor. We also used rare earth salts, so like cesium salts and a couple other things. Microspheres, okay, which are just basically these little, you know, teeny tiny plastic particles, which there was a method to that. We basically wanted to see how far they would get transported because they were roughly the size of some of the microbes that the microbiologists were really interested in. So we wanted to see how far are they going to get transported, okay? And they haven't gotten any data back yet about that, so I don't know the answer to how far the bacteria travel. And then we also, at the very end, we did a 24-hour freshwater pulse. So we just pumped in fresh water for 24 hours. And so what did this tell us about the effective porosity? What are our results? Okay, and I won't belabor you with all of the, because this took a long time. We injected in 2010, we went back in 2011, 2013, and 2014 to collect data from the corks, and this is the results of just the sulfur hexafluoride. Basically what happened, here we injected, we actually saw a little bit of backflow, which they kind of expected, and there's a reason for that. It has some bizarre hydrogeology thing, but for the most part, it went to the north. Okay, so good. Our idea was mostly correct. We were basically able to see that we had a general northward flow pattern. Also interesting, the speed we calculated at about 2 to 3 meters per day. Okay, so that's how fast the fluid is moving in the subsurface, more or less. And that's a lot higher than we had expected with numerical modeling, because they've been modeling this area for a long time. But to get a speed of 2 to 3 meters a day inside the crust was very high. It also told us that our porosity is less than 1%, and that we're probably seeing channelized flow. Okay, so basically it's not the porosity that's important here, but the permeability, the connectivity. So there's probably a lot of fractured zones. The crust is probably very heterogeneous. It's not all the same thing. It's not all the same, basically, structures, and there's a lot of easy places for water to get through. So that was kind of a neat that was a neat project to work on, even though it wasn't for my PhD, because it really gave me the ability to go from, okay, here's the problem, here's the engineering we had to do to try to solve the problem, and then finally, 10 years later, we get the results, which is really cool. So why do we actually care about the seafloor, and specifically, why is studying the deep sea important? So I don't know if any of you have ever seen this cartoon before. It's very famous. It was from the New Yorker, and it's just ladies who lunch just sitting around saying, I don't know why I don't care about the bottom of the ocean, but I don't. And I feel like that is kind of the prevalent opinion in most of society. And if you really want to break it down, we should care about, okay, here we go. So this is, remember those little word association things I gave you guys? So I plugged them into a word cloud, and this is what you guys said for nouns, okay? So, water, okay, obviously, all right, so sharks, waves, fish, okay, these are all reasons we need to care about the ocean, okay? So whales, dolphins, all of these things are important, okay? Yeah, some of them were not terribly creative, but I love you anyways. Shh. Okay, and then when you look at the adjectives, some of these were really great. I really liked, so peaceful, cool, large. Where's the deep one? There's vast. I really liked that one. So these are huge systems, remember. Remember that the ocean is 70% of the planet, okay? We live on the minority, okay? The majority is what's going to be affecting us, okay? And that really comes out when you start to look at news headlines, okay? Every time there is a new scientific expedition or somebody goes out and does something in the deep sea, we find out something new, okay? And that's why the deep sea is really, really, really important, because we don't understand it. And therefore, we don't understand how it interacts with a climate system. We don't understand how it interacts with us, okay? What are we doing to it when we do certain things? So for example, things like anoxia. Okay, so climate change is basically driving some basins to be suboxic or anoxic. So there's no oxygen, which means very, very little can live there. And so I was on a Nautilus cruise a couple summers ago where we went out to some of these anoxic basins, and they're right off LA. They're right off LA and San Diego. And so there's no fish there. And so that's bad for fisheries, right? And so that's bad for our food supply. Other things like ocean acidification. The ocean acts as a buffer. Okay, so what happens when carbon dioxide interacts with the surface ocean? It forms bicarbonate first, okay? And if there's too much bicarbonate hanging out in the water, then it's just going to get really, really, really acidic, and none of the little animals that make shells out of carbonate are going to be able to make their shells. And so we've actually seen this happening in oyster farms up, I think, near Tamales Bay in California. And I have a colleague who's working with the oyster farmers to do things with seagrass to kind of bring their local acidification levels down. Other things that are really important, things like, sea sponges, okay? Things that we don't know could potentially be cures for things. I know there's, what's that one ad for the drug where they're like, oh, for the thing that's found in jellyfish. It was originally derived from jellyfish. That's a thing. So if we don't know about what's in the ocean, we have no idea how it could potentially help us in medicine and all kinds of stuff like that. At the base level, pollution. I'm sure you guys saw the picture of the beer can at the bottom of the Mariana Trench, or the plastic bag. I think it was a plastic bag. That's a thing. That was not fake news, that was real, okay? And there's actually, the Japanese agency has a database of pollution in some of the deepest trenches. And so that one's been archived, and yeah, it sucks that it's there. So this is, again, why we really need to start thinking about what are we doing as humans to the ocean, even if it's as inadvertent as using body wash with microbeads in it, okay? And I know that microbeads are being phased out, and that's great, but microplastics are still a problem because they're still being consumed by by sea life. Okay, and that again affects fisheries. It affects the ecosystem. Okay. Okay. So fundamentally, we still really don't know a lot about the deep sea. Okay, even though, yeah, we've got these cool tools, we've got submersibles, we've got ROVs, we've got AUVs, we still don't know that much. And there's actually a concerted effort right now, it's called Seabed 2030, and there's an effort to map the entire seafloor, I believe at a 5-meter resolution, which is pretty good, by 2030. And how they would do it would be to send out a bunch of those AUVs, and they would go out and collect data and then come back, and then we'd send them out again. So there's an effort to do this, but we're really far away right now. We don't have a lot of data. So even though, like for example, hydrothermal vent systems were only discovered in 1977. Okay, so that's 40 years ago. And even in those 40 years, you would think, oh yeah, 40 years, Katie, that's like tons of time. You know everything about vents. We know almost nothing about vents. Okay, we still know very, very, very little. They are very hard to study. And we really, really need to keep developing technology so that we can keep studying them. There's new cabled observatories where we basically have a fiber optic cable that goes out to the seafloor. We can plug instruments into that. That eliminates the battery issue because we have power all of the time. It also eliminates the data storage issue, because then we can tap into our instruments all the time and continually recall our data and say, hey, what's going on this week? Like one of our corks is actually hooked up to one of these cables. So when the huge earthquake in Japan happened a number of years ago, the first thing I did was log on to the Ocean Networks Canada site, and I was able to watch the tsunami wave go over the cork, because I could see the change in the pressure as the water column height changed, which that was really amazing for me, to actually have real-time access to my data. Normally, I would only get data once a year. Okay, we go out once a year in the summertime. So only by continuing to explore the oceans can we move towards a better understanding of how the planet has evolved through time and how human activity is affecting the deepest parts of the world's oceans. Okay, so we really, really need to keep working on this, and under the current funding climate, it is very difficult. I will not lie, I have been unemployed for 3 years from permanent employment. But I don't want to be a downer, so I want to leave you with some cool stuff that's being worked on. I have some colleagues at Woods Hole who are basically working on underwater wireless, okay? And the goal of this project is to basically eliminate the need for a tether between the ROV and its weight, and its clump weight, okay? So it could be free swimming in the water and still transmit data. So what they've put out is a blue laser, and then basically they're able to transmit data in and out of the sub. So they're watching this inside the sub as this is flying around. And so this originally was, I think, 1280p. Yeah, I've scaled it down for this talk. But basically, we're now able to transmit data fast enough, and it's going to be great for working with ROVs, because if we don't have that tether, then we remove one more safety issue. We don't have to worry about the vehicle getting hung up on anything. It'll be easier for the pilots to work. So this is a project that's ongoing. It's very engineering heavy, but they were using some of my instruments as like a test bed. So like they'd hook one of their sending devices onto it, and then they'd send down basically a CTD or a wire with one of their receivers on it. They'd query, and they would be able to get all of my data in like 30 seconds. And I was really jealous, because I'm like, that would normally take me an hour and a half, and you did it in 30 seconds. So their data speeds are really impressive. And part of that is because the clarity of the water at this depth is so nice, very, very clear. Not a lot of particulate matter. Okay. Come on. Okay, and then I want to dispel a rumor. Maybe not a rumor, but a conception, a misconception I would like to dispel. How many of you think you need to be a genius to get a PhD? Or like wicked smart, like uber wicked smart? Okay, some people. So you don't have to be. I'm not a genius. I'm not wicked smart. Like, I'm pretty smart. But what it comes down to is perseverance, okay? And so this is a great diagram that I feel like walks you through this. So imagine this circle is all of the human knowledge that exists right now. And so you get a little bit in elementary school, you get a little bit more in high school, and then when you go to college, you get a little bit more, but you make a little bump because you're specializing, right? You're going to have a major. And then if you go get a master's degree, you make that bump a little bit bigger, okay? You're expanding into your specialty. And then if you keep reading papers and you maybe start going towards a PhD, you're going to get that bump all the way out to the edge of what we know right now, okay? And if you keep pushing, if you just push at the edge of that knowledge for a couple of years, you might make a little bump on the outside, okay? So you're expanding our current human knowledge, okay? So that little bump, that's PhD. Okay, you are just taking one little bite out of what we don't know and adding it to what we do know. Okay, and so then, of course, your perspective changes, and now you're in that bump, and you're like, whoa, I could go anywhere. It's amazing. So you have to keep pushing. Okay, and that's really, really, really important. If you want it bad, just keep pushing, because that's honestly how I got there. And I'll take questions.
15 minutes.
Okay, Kristen.
How did you pick the location for putting the several forks together?
How did we pick the location for putting... Okay, so initially, before they had decided to put in the corks, they had been... I think they were on a completely unrelated cruise and had just happened to notice that the heat flow had a certain pattern around these two outcrops, that one was sucking in the water and one was blowing out the water. So they initially were like, okay, we should look at that. Let's get some fluid chemistry. Let's take some samples, some sediment cores, just little things. And then they bolstered their hypothesis that, there's fluid going in here and it's coming out here. Is this the same system? And then so setting out to try to address that, that was when they decided to put the corks in between. Yeah, that's a good question. This was a very, very long process. Deep sea work usually is. Yes?
So with water really high Pacific heat, does climate change have a huge effect or small effect on what's the ocean floor? And what sort of changes?
Okay, so the question is, does climate change have a large or small effect on the sea, on fluid in the crust, things like that? It's a good question. I would love to answer it for you. We don't know. And that's one of the things that people are working on right now, is really understanding how the fluid that circulates around inside the crust, how that fits into the climate change paradigm, because we really don't know what its role is right now. Is it removing any amount of carbon dioxide? Are we getting sequestration by certain microbes that metabolize in a certain way? We're barely scratching the surface of that right now. So good question. Okay, I'm just going to keep going like opposites here. So I saw, yes?
So are there any known environmental or ecological impacts or detriments or harms of like boring and corks specifically, because you leave those in for so long?
No, actually not really. So the area that we're working in, most of it's a bare sediment, well not bare sediment, but it's a sediment bottom. And it has lots of those sea pigs that I like, okay? It's got a lot of sea cucumbers. They actually are really good for octopi, apparently. So every time we show up at a cork, there's always a family of octopus living on it. So we like to feel that we are providing a safe habitat, at least for some of the local life. Really, because all we're putting down is just steel, okay? So what happens with steel when you put it in salt water? It rusts. So effectively, all we're really doing is adding extra food for any iron oxidizers and microbes and stuff like that. So we have not found any detrimental, at least nothing major anyways. And when we're always very careful when we actually penetrate into the rock, because we want to be taking pristine samples for the microbiologists. So there's a lot of quality control and making sure that we're doing things in the right way and we're not just dumping a whole bunch of crap on the seafloor. So that's a very good question. Yes?
How'd you deal with seasickness?
How did I deal with seasickness? I do not get seasick. I was very, very lucky in that respect. I did a tall ship cruise when I was in high school with the Sea Education Association, and they also do college programs. You could spend like a couple months on a tall ship doing science, and then some on shore learning about marine science. But yeah, I don't get seasick. Oh, one thing I wanted to tell you guys. How do you think we pee in the submarine? Diapers? That's a good one, but no. We're actually not allowed to wear anything synthetic in the submersible because if there were to be a fire, it would just melt to you and that would make it much worse. So we have to wear wool, cotton, natural fibers, so no fleece, all that kind of stuff. So I don't pee in the submarine. There's actually a big sign in the galley on the ship that says "Pee before you go," like a license plate. And so it reminds everybody to pee before they get in the sub. I don't pee in the sub, but there are bottles. And obviously it is easier for the gentlemen to pee in the submarine than it is for the ladies. But we get Lady J's, which are really handy. But I don't pee in the sub. But I just thought, you know, we're at camp and you guys might get a kick out of that, Augie.
So when you're talking about how you get down with the submarine, and then when you need to go back up and drop the weights, do the weights just stay on the bottom?
They do. They are just scrap. They're scrap iron. So it's, yeah. So you can tell when and we try to be really cautious about where we're dropping them. We don't just drop them in the middle of a hydrothermal vent field. We drive away from where we are working and drop weights. But this is a consequence of working in the deep sea. You cannot go down and basically come back up without having some kind of weight loss because it would take too much power to basically drive back up to the surface. And current battery technology really doesn't allot for that. Oh my goodness, so many questions. I'm so happy. Oh my goodness. Okay, all the way in the corner.
Yes. You said that you injected stuff into the sub ocean floor.
Yeah. Mm-hmm.
Stuff like SF6, 24-watt freshwater pumping. But weren't you suspicious or like aware of the effects it may have on the natural environment like marine life? Were there any effects at all?
Well, so the question was the stuff that we injected into the crust. Would it have any effect on the life living in the crust? Well, it turns out that, at least according to my microbiology colleagues, it really didn't. So they still found tons of microbes living in the subsea floor, and they've still been able to culture, all kinds of stuff that they did not expect to be there. There's a guy who's working specifically on viruses that live in the crust. It turns out there are a lot of viruses that live in the crust. And he basically had to set up a pump that would filter water, and we left it there for like a week in order for him to get a big enough sample. But so far we haven't had any adverse detrimental effects.
And like, can you use the codes that you put in to like predict changes in the ocean to like underwater eruptions or tidal changes and stuff like that?
So the question was, can you use the data that we collect with corks to look at changes in the ocean, things like eruptions? Really cool thing, that was part of my PhD. So you can actually see earthquakes in the fluid pressure data. So when there's an earthquake, depending on if you're in the compressional or the dilational part of the field, you will see either a pressure drop or a pressure increase. So we can see things like that. Things like the tsunami wave going over, that was a pretty big thing. We actually saw some large earthquakes that were pretty far away. We saw them at a really low level, but so we can do some level of observation. Yeah, yes, you've been waiting.
So you just said, for example, you saw some data, critical data. Where can we, search for that data? That we can see with our own eyes, a website or?
We don't. Okay, so the question was, where can you guys see the data? Okay, so if you're, okay, there are a lot of papers published on this. If you just basically search cork, cork research or whatever, you will get a whole bunch of PDFs for sure. That's one way. If you want to look at the data live, Ocean Networks Canada, okay, which is the cabled observatory that comes out of Victoria, British Columbia, they have a data portal where you can, as a member of the public, just go on And I think you have to make an account, but it's free. And you can say, oh, I would like, we only have one cork hooked up to it. So you can say, oh, I would like to look at the pressure data from 1026B from June 1st through July 2nd. And you can query that. It will give you, an Excel spreadsheet, or, it'll make a graph for you, things like that. So these data are your data. And this is something that we really emphasize in our field, is that and there's a big push in marine geoscience to do this right now, is to get all of our data out there as much as we can. And sometimes it's a little harder. All of the drilling data, if it's older than 2 years, there's a 2-year moratorium on publishing data. If the drilling data is older than 2 years, it is all available on the internet, okay, through the IODP website. Okay, so if you want to go look at some cores that were taken in the, in the 70s, you can do that. There'll be a core description and things like that. So, yes, in the back.
So we've got 2 questions.
Sure.
My first question is, why can't you use like radio signals in the ocean to communicate with
Okay, so the first question is, why can't you use radio signals? Because it attenuates in the water column, like right away. So yeah, it would make it like a foot. Okay.
So why do you use yellow and not any other like similar kinds of
Oh, for the vehicles? I think, so the question is, why do we use yellow so much for vehicles? Part of it is for visibility. That's mostly for visibility. So things like safety orange, safety yellow, those are really commonly used for basically anything you throw in the ocean. You'll see buoys that are that color, mostly because it's highly visible from, not just at the surface, but if you're a ship, you're going to be able to see it from a good ways away, and so you won't run over it, that kind of thing. That was a good question. Okay. Oh my God, you guys have so many questions. Okay. Okay, Zoe.
What is the effect of the force of particles released from an underwater volcano?
Okay, sorry, what was that again?
What is the effect of the force of particles released from an underwater volcano?
Aha, what is the effect of the force of the particles released from an underwater volcano? Okay, so we haven't actually been studying the explosive volcanic eruptions for that long, so I don't have a good answer for you. But the great thing about water is that it's an incredible buffer, okay? And not just for, carbon dioxide, but also for temperature and for force. So I would imagine that if you were not, if you were not terribly far away from that, that super explosion or eruption that I had up there before, you'd probably be okay. For things like temperature and hydrothermal vents, we can actually get really close with the sub, because the bottom water is 2 degrees C, and even if the fluid coming out is maybe 180 degrees C, we can still get pretty close. We don't want to get too close, because the windows are still made of plastic, so we don't want to melt them. That would be very bad, and we would die. So I don't have an answer for you, but that's something we're working on.
The environment, because on the land volcano, a huge cloud of soot and particles comes up, they're just in the air, so you want to
Yeah. So probably if you're in an explosive eruption, there's probably not going to be much on the bottom around there anyways. So you're probably not drastically affecting the community. Also, the great thing about when there are eruptions on the seafloor, and this happens at the mid-ocean ridge, you actually get recolonization of the new eruption fairly quickly, within a couple years. So one of the things that we don't understand right now is how larvae populate the different mid-ocean ridge hydrothermal vents, because we have no idea how they get from vent to vent. Do they lay dormant and then they like chemically sense something and fall out, or we have no idea how that works. But repopulation happens pretty quickly. And Ernesto, you've been waiting very patiently.
So we know that in the air, like when we are in the car, when we are, the soil and everything is so different. We have a huge variety of soils.
Mm-hmm.
Does that same thing happen in the ocean, or is just this?
Or is it all the same?
that you were
Okay, that's a good question. So the question is, like terrestrially, we have very different kinds of soil in different places. Is it the same way in the ocean? And it is. So some places have what we call a carbonate ooze, which is made out of mostly tiny shells of dead critters that used to live in the water column that have rained out. We call that marine snow. Some places where it's too deep for those things to, we have something called the carbonate compensation depth, where below that depth all carbonate dissolves. In those areas, we get something called red clay, which is basically what it sounds like. It's red clay. And then there's silica oozes, so like diatoms and things that make a siliceous test. When those fall out, they'll create a silica ooze. So it really depends on what is making the sediment. Are you getting a lot of outflow from a river? Then you would get a lot of terrestrial stuff added in. That's usually just near the coast. So things like that. But that's a good question.
One more question.
Oh my God, okay. Okay, yes.
How do you make a long distance phone call in the HOV?
Oh, how do you, I was waiting for that, thank you. How do you make,
And think and drink in there.
okay, so two parts to this question. One, and I'll do the easier one first. Do you eat and drink in the submarine? Yes, they pack you a very delicious lunch. I usually forget to eat because I'm working so hard, and then suddenly the pilot will be like, we only have like a half hour left of bottom time, and I'm like, oh crap, we still have 3 things to do. So we do all our stuff, and then I usually eat on the ascent. But yes, they give us a really good lunch, and there's water, and the cooks treat us really, really well. It's great. And then the second part was, how do you make a long distance phone call in the submarine? Which is a very good question. You don't. So here's the thing. In the entire history of Alvin, there have been 5 number 2s. And so the sub has been in operation since the 60s. And to quote a pilot who is not my boyfriend, someone else, the options are limited and horrifying. It basically involves a trash bag. And I will leave it at that. So yeah, we don't. Yeah, you don't. So I mean, like some scientists like practically dehydrate themselves. I don't really have to. I just don't drink coffee in the morning. If I'm diving, it's not a big deal. So it's different for everybody. I will be around. You guys can ask me more questions at snack. It's all good. Thank you very much, guys.